All right, we're going to kick this off with learning what the universe is made of from Manu Schaan and Phil Marshall.
Great. Thank you so much for having us today. We've talked about the universe on a number of scales so far, and this talk by Phil and me will be about observing the universe on the largest possible scales, and this is what cosmology is. There's been also questions of, what are exactly the science questions we're trying to answer, and what are the modalities of our data sets? And so the hope is that Phil and I will take you through a number of these to give you an idea of what kind of data sets, what kind of observables we have. So I'll do the first part, which will be a 7-minute trip to the edge of the observable universe and back. So I hope you're ready and have fastened your seatbelts. I'll try to motivate why cosmology and astrophysics is a place where you should spend your time developing your data science methods, and why some of the most fundamental questions in physics, I would argue, are to be answered there. And Phil will focus on some of them more specifically and some of the inference methods that are being applied. So to get us started, we've seen this diagram in a number of forms so far, but this is basically the timeline, the history of our observable universe with the Big Bang all the way on the left and us right now all the way on the right, 14 billion years later. And there's many different observables that we have access to that can tell us something about the composition or the evolution of the universe. But some of the ones I would like to focus on today are the so-called cosmic microwave background. So this is the very first light that was emitted after the Big Bang, and you can think of it as the baby picture of the universe. This is a 2D spherical image that gives you the statistics of the initial conditions of the universe. And much closer to us today, about 14 billion years later, the second big class of observable I wanted to tell you about is what we call large-scale structure in the universe, meaning how the matter and how the galaxies in the universe clump together to form structures. So on the left, you have the initial conditions of the universe. On the right, you have the present conditions. And much of the game of cosmology is to try to match the statistics of the initial and final conditions. So what you have to do is evolve those initial conditions through 14 billion years under gravity and try to match the final ones. If you succeed at this, you may think you have a good model of the universe. And we currently are in such a position. We have something we call the standard model of cosmology, fits a large number of these observables. A very successful model, if you wish, except for the reason that it relies on a number of components. One, dark energy, which Phil will tell us much more about. But if your retinas fire when you see a violation of Newton's laws, your retinas should be firing really hard right now. The other component that we've heard about already is this dark matter, this matter that we seem to see only through its effects, its gravitational effect on the rest of the universe, but 5 times more abundant than the rest of the matter. And then another very interesting class of questions that I've grouped under the term inflation really are about what processes generated the initial conditions of the universe. And as a physicist, you may be surprised that we're asking such a question. Normally, the initial conditions are given, and our job is to perhaps evolve them forward. But in this case, there's a lot to learn about what happened before this cosmic microwave background and generated these initial conditions. So to summarize, the cosmic microwave background, initial conditions of the universe, the same fluctuations we see in the cosmic microwave backgrounds evolve into the 3D clustering of matter and galaxies in the universe. And when we match the two, we are, so far at least, there's no model that really avoids this, that the ordinary matter that you and I are made of are only 5% of the total budget. Dark matter is 5 times more abundant, and the dominant part is this dark energy. So I just wanted to take a minute and emphasize that we're not just lightheartedly adding components to the standard model of particle physics. This is very serious that we're claiming there are 2 new forces of nature, effectively, this dark matter and dark energy, that have not been seen in any other way. And the nature of dark energy and dark matter are perhaps some of the most important questions in all of fundamental physics, so much so that the whole US particle physics community concluded that the highest priority particle physics experiment for the next decade was actually a CMB experiment. So these are really important questions that we're trying to address. And just to put this all together from what we heard about our local perspective in the Milky Way, all the way to the CMB and the edge of the observable universe, and also to give you an idea of the kind of data sets we're dealing with. This animation here starts us around the sun and then zooms out. And this is all actual data. So the sun, only one of many, many stars in our own galaxy, the Milky Way. And as you keep zooming out, you see more galaxies of order 100 billion galaxies in the observable universe. Each of these is actual data, and in fact, very outdated data. We have much larger catalogs. And as you keep zooming out or going backwards in time, you get to this cosmic microwave background, the edge of the observable universe. So if you're trying to think about what's the modality of our data sets, really there's this observable universe, this sphere that you can hold in your hand. You and everyone you know is right at the center, and all the observables we have are effectively either 2D maps of the sphere or slices inside, 3D positions of matter, or 2D projections of those 3D quantities. And these are a lot of our cosmological data sets. I talk about 2D projections of 3D distributions of matter, because in fact, as you may guess from this picture, all the light we see from the cosmic microwave background, this first light from the Big Bang, for us to see it, it has to travel through the whole universe for 14 billion years. And as it does, it will encounter galaxies. This is very interesting because those galaxies will imprint shadows on this backlight of the cosmic microwave background. And these shadows tell you information about galaxies that you could not see by just looking at their stars. Some of these shadows have to do with gas, which is the dominant component of matter, of ordinary matter. So if you think you've seen those beautiful spiral images of galaxies, this is about 5 to 10% of the whole ordinary matter. The rest is this much more extended gas. And other forms of lensing have to do with gravitational potential, an effect called gravitational lensing, which tells you a projected map about the whole matter, the whole mass in the universe, both dark and ordinary. So these give us projected 2D maps of the 3D density, and we get to observe the matter in many different ways: the dark matter, the ordinary matter, the gas density, temperature, etc. So in my last minute or so, I just wanted to briefly mention what some of the frontiers were in being able to use those data sets to make inference on these important questions. Starting from the cosmic microwave background, and the theme here would be non-Gaussianity. When we observe the cosmic microwave background, we're observing it from the Milky Way, our own galaxy, and that's a foreground that we try to disentangle. Just how well we can do this is a critical question, because it will determine how well we can answer questions about this inflation, those initial conditions of the universe. But our own galaxy is not the only obstacle or the only foreground. We have all these other shadows that I talked about with those cryptic 3-letter acronyms that I'm showing here. Those are foregrounds that we also want to distinguish or extract, because they all contain independent information about our universe. So non-Gaussianity as a nuisance, but also as a signal. And this is sort of where we need to make progress. In the case of a large-scale structure of the universe, again, non-Gaussianity is also a bias and a signal. The evolution under gravity for 14 billion years of those initial conditions just produces non-Gaussianity because it's nonlinear. And any nonlinear operation on a Gaussian variable makes it non-Gaussian. In fact, the non-Gaussianity of the final conditions is a challenge for us to extract cosmological information, but the non-Gaussianity of the initial conditions would be a really important discovery. Finally, what I'm trying to show in this animation from a cosmological simulation is that the properties of the dark matter that you see here in blue do not match those of the ordinary matter that you see here in red and green in these fireworks. And the fact that our tracers of the universe actually only trace one or the other is one of our big challenges. So we'll switch now to Phil.
Okay. All right. So for the second half, I thought we'd wind back and talk about something that Manu mentioned, but then kind of skipped over a little quickly. Where's the screen that does the?
Sorry about that. The screen's above. So your mouse is here.
Oh.
Sorry. Is that okay?
Let's see. Okay. So here's a version of the same picture that Manu showed you. This is the one that I prefer. You notice that in this diagram of the expansion of the universe, the lines aren't straight. You see that little bit of curvature at the end on the right-hand side? That's a reminder that the universe expansion is accelerating and not just coasting along. So I was pulling Manu's leg earlier, right? He's moved on from the problem of dark energy to think about non-Gaussianity. But just to spell it out, this is weird. We were expecting the universe to collapse under its own weight, for everything to fall back together, but it's not going to do that, it seems. It's going to expand forever at an accelerating rate. So you were taught that what goes up must come down. Turns out it's not true when it comes to the whole universe, and nobody knows why. Okay, so we're going to put some effort into reconstructing the universe's expansion history, try and make a measurement of this dark energy effect, try and figure out what it is. Here's a simple picture for what's going on as the universe expands. Think of galaxies as raisins in a lump of dough, which you bake, and then they all expand apart from each other. And the thing that we can measure, or try and measure, is the expansion rate as a function of distance, or otherwise known as the distance redshift test. So we can try and measure the apparent recession speed of galaxies, one way or another, and compare that to the distance of those galaxies, one way or another. And then the function that describes that relationship between distance and speed, it's called the Hubble function. And it used to be a simple function, it's not anymore. It's complicated by the noted presence of this dark energy component. So this is our program, to infer cosmological parameters that describe the properties of dark energy from measurements of distance and apparent recession speed of galaxies in the universe. Okay, so it turns out that you can use type 1a supernovae as a way to measure distance in the universe. They're all approximately the same luminosity, so how bright they are tells you how far away they are. We can measure their apparent recession speed using the redshift in the spectra. The ones that are moving away faster from us look redder. And so here are some pictures showing that we really can do this, and we really can infer cosmological parameters from some sample of type 1a supernovae. Turns out the same thing is true for objects called strong gravitational lenses. They tell you a different kind of distance in the universe, a time delay distance. But again, each one of these systems, a galaxy acting as a gravitational lens to a time variable source in the background, can be used to make a measurement of distance in the universe. So we can do the distance redshift test with these two types of objects. And we have been doing that with some success. So where are we now? We're coming to the end of stage 3 in the program, the kind of global program to try and measure dark energy better and better. And here's what we've been doing in stage 3. We've been building up samples of pretty impressive size of these objects and inferring cosmological parameters from them. And we've been making some shortcuts as we go. Here on the right-hand side are at the top, there's an expression for the log likelihood that you use when doing stage 3 cosmology with supernovae. And down at the bottom, there's some indication of how we've been using strong lenses, measuring distance for each one and pretending that each one gives an independent measurement of distance. So what's next? We are in the process of scaling up for Rubin's LSST. You heard about this a couple of times today. By the end of the survey, we should have something like 400,000 supernovae to use, and maybe 3,000 time delay lenses. So these are orders of magnitude bigger samples than we've been used to so far. So fantastic opportunity for high precision cosmology. And the program is to model each object. For example, scaling up in our group at KaiPAC, looking at the strong lenses, means using simulation-based inference via neural posterior estimation for the speed up that we need object by object. That's important to us. And then also trying to increase our model for lenses to try and mitigate domain shift. Domain shift is called model bias in cosmology. And then we try and hierarchically infer cosmological and nuisance hyperparameters, and that's our way of accounting for distribution shift, or in cosmology known as assigning the wrong prior. Okay, so stage 4, cosmological inferences are inherently hierarchical, and so what we're trying to do is model the populations explicitly. And here's proof from the literature, a nice PGM showing the hierarchical inference from supernovae. My PGM skills only extend to much simpler versions on the right, but that's what we're doing in strong lensing. And I crossed out cosmological here because it occurred to me on the drive in this morning that I think we can claim that all astrophysical inferences are hierarchical. We're interested in the physics parameters, which are hyperparameters, not the individual objects, which typically we don't really care about. Okay, so is this true? Are we actually going to do hierarchical inference? Well, it's hard to get away from the traditional approach because it's so convenient to compress the data into summary statistics and then just do single level inference. Maybe that will persist. Maybe we can show that we can do that with sufficient accuracy. It's to be seen. And then for a last slide, Manu mentioned that the next frontier in cosmological inference was non-Gaussianity. And he was talking about non-Gaussianity in the parameters. So the initial conditions of the universe is a set of parameters to describe the universe. But I think we should be thinking in terms of none of our PDFs being Gaussian, really, when you look closely enough. And it might turn out to matter that we model all of our PDFs in our problem in some non-Gaussian way to some extent or another. And that's the kind of thing that we might need help with to do that well. And I think that's what I'd leave you with. Thank you.
Thank you, Phil and Manu. Questions? Go ahead.
Hey,
Yeah.
Can you say more about, I guess, why you think the non-Gaussianity is a thing and how you might be measuring? What signals are leading to that?
What leads to us thinking that non-Gaussianity is going to be important? So we spend a lot of time doing verification tests in our group. Because we have this big speed up with the neural networks, we can do experiments where we model thousands of systems and check for, did we get back what we put in? And Sydney's been doing a lot of this in the last couple of years, and she starts to see cases where there are some residual biases in the hyperparameters. We don't get back the hyperparameters we put in, and it's because we think we've been assuming Gaussian PDFs for, in particular, the conditional PDF in the middle, which isn't quite cutting the mustard. And so from that's sort of making us think, well, maybe we should be paying attention everywhere. The reason I flagged the non-Gaussianity in the sampling distribution for the data, that's maybe coming more from some of the large-scale structure inferences, where people have been using Gaussian likelihoods for a long time, but a few years ago started thinking, well, maybe it's not quite exactly Gaussian. Maybe we should be doing something more sophisticated. So I think this probably is going to keep on going. We're going to have to keep an eye on it.
Maybe if I could add an element of answer. Right. Yeah, in the context of this large-scale structure, so if you look at the cosmic microwave background and those initial conditions of the universe, other than the foregrounds like the Milky Way and other sources we need to extract, that signal appears to be very, very Gaussian. And so life was easy for CMB physicists. You measure a power spectrum, you have all the information. But when those fluctuations evolve and collapse under gravity to form galaxies, that process is inherently non-Gaussian. And so far, a lot of us in the large-scale structure community have mostly been using power spectrum tools to describe those non-Gaussian large-scale structure. So that's one place where our Gaussian information got spread out into non-Gaussian statistics we haven't explored. The other one is looking further down in this cosmic microwave background at deviations from Gaussianity in those initial conditions. And this would tell us something about the particle physics of those quantum fields in the early universe.
Cosmology specific questions for Phil. So yeah, in your group you're really looking into the hierarchical inference, and I was wondering if you think there are some aspect of that we could translate to like the other probes, like the weak lensing and LSS probes, where we just, as you say, go from the summary statistics to the cosmology. Like, are there things that can be applied?
Yeah, so I think there must be. All I have for you right now is this kind of general hunch that it's worth doing, because when you do unroll the summary statistics and do the hierarchical inference in full, you're allowing for more structure in the data to come out and not be swept under the carpet. But for specific things, it could be that some of our experience with how hard it is to do hierarchical inference in practice are also going to be useful for people trying to do field-based inference in weak lensing or something. And those problems of how to do that in practice are, again, something where we could really benefit from collaboration with other folks in the center, I think.
All right, awesome. Thank you.
So it's an abbreviated version of a longer talk, but hopefully some of this is interesting and or useful. We'll see. We can credit or figure this out after. From even the last presentation, it's clear there's sort of many different ways of thinking about what it might mean to have a distribution shift. Broadly, when I say distribution shift here, the way I'd like to think about this is that in most machine learning problems, what we'd like to do is to train some model that we can then deploy in the real world. So, the way that we often think about lots of statistical estimation, machine learning, sort of all these frameworks, are that we hope this is sufficiently true out of the box such that things work. As maybe many of you already know, despite the fact that we teach and often think about things this way, this is actually almost never true, right? So, as you might know, there's almost always some difference from when you construct and train your model to whenever you get to deploy it, and these shifts can cause significant issues for whatever model you're trying to build. So changes in the data that can come from lots of different mechanism changes, all the way from different kinds of data problems. I'd like to learn more. I think you gave some examples in the last presentation, but seasonality changes and data all the way through different kinds of just confounds can break training to deployment. And so I'm showing one example from sort of recent-ish paper where they looked at, this is a sort of constructed example, but it matches well a lot of how the field was thinking about how we might model distribution shifts for a long time and sort of implement them in the real world. And in particular, get at, I think, some of the interesting questions where could we actually come up with methods that are robust to any kind of distribution shift? I think there was a lot of interest in sort of worst case robustness, no matter what happens in the environment or in the world. So this example is it's constructed, but it's interesting. What happened is ties to an observation that sometimes in learning problems, the model picks up on the background and not the object that you're interested in. And so here, if you're interested in classifying the kind of bird, and it's known to be, I guess, urban versus sort of forest bird, you might intentionally modify where you place it. And so this is a sort of cartoon example where the object was placed, sometimes awkwardly, in the second example, in an intentionally different environment. But awkwardly to us, machine learning models out of the box will often get fooled by this if the correlations or the nature of the data they're trained on are such that birds, species or types always strongly correlated with their location. And so they pick up that correlation at prediction time, they essentially would use the background for prediction as opposed to the actual object. And so this is something that the field is trying to protect against, and there are a bunch of these examples trying to engage with this question. And so one of the questions that animated the field when large language models and foundation models became a thing was whether these were still problems. And this is the premise of the title of the talk, though I didn't get a chance to set it up completely. And what I mean by this is what was observed was that many of the distribution shift issues, including things that look like this, seem to work out of the box when I used the foundation model. And this was, depending on where you stood, either incredible, like you've solved a bunch of these issues that were plaguing deployment of machine learning systems, or terrible because hundreds and thousands of papers and people's efforts are now useless because apparently we can just solve these things by sort of having really big foundation models. And I'll say a bit more about what foundation models are if you're not familiar with them in a couple of slides. But it's hard to overstate at least some of the sense when talking to my colleagues on some of what we observed when a lot of scaling effort was happening in the field and how this seemed to change the paradigm in how to think about distribution shift issues. So my main goal today is expanding on a line of work that we've been building recently to try to sort of help the community engage with what it might mean to build machine learning models in practice, and sort of different ways the distribution shift issues can come up, and sort of some sense of a taxonomy that might help think through the problem, and the cases where we have some solutions, anchor on those solutions as ways to maybe help frame how we might think about things. For time, I will mostly talk about just sort of that last portion. I do a little bit of a punny thing in the beginning of, do you believe there's distribution shift? And I just do a cycle. There's always going to be distribution shift. Now, there's a different question of, does it matter in your context or not? Again, one of those things that I'll skip. So maybe at some point we might do a longer version of this. OK, so my goal here now would then be to go through some of the latter half of the taxonomy, to go through some of the tooling that exists. And part of it is tooling, part of it is just better understanding of the tools that we already had available and when they work and don't work, that may be informative for some of the contexts that hopefully might come up in the course of some of the work that we're doing. So in particular, I think one of the most fascinating observations that I think has been better understood more and more is really the power of fine-tuning as a way to handle some kinds of distribution shift. And so the path in the tree here is, you have some distribution shift issue. You're interested in, we're calling it extrapolation. I'll try to give a little context of what that means in a second. And I have data that's relevant for the target domain, and sufficient enough data that I've done a bit of maybe pre-training. So I have some large model, and I have data that I can use to solve close to the task that I'm looking to solve in practice. And so this is the place where fine-tuning tends to shine. And this has been combined very, I think, effectively with the hammer in machine learning, which we often call empirical risk minimization. Effectively, this is machine learning 101. So I take my data, I combine a bunch of different data sets together, and I just sort of train a big model on everything. So the key idea here is I'm not doing anything special. I'm not doing any kind of special mechanical thing behind the scenes. I'm doing sort of what you might do in literally your first machine learning project that you ever did. And it turns out, this is the principle behind foundation models, again, at scale and across lots of different contexts all at once. The effect that this has is that the model gets to see a bunch of different, if you like, distributions. And what we found is that this seems to be pretty good for getting models to learn good features such that if I then try to fine-tune to a particular target task, they tend to do a good job in prediction. One example that I found sort of compelling that uses this paradigm is some recent work that asked this question of, if I'm interested in robustness to various kinds of spurious correlations, as we've alluded to a little bit of, in some examples. So you can imagine the spurious correlation of the background for the bird example that I gave. There was I think, initially quite surprising paper in late 2023 that argued that, again, people had done lots of different methods to handle this problem, many of them quite sophisticated. But they argued that if I just sort of took whatever model I already had, fine-tuned the last layer on the target task, and reweighted appropriately, this actually did a pretty good job. And in fact, competitive or better than most of the more sophisticated techniques for solving this problem. Over time, we have a slowly better and better understanding of why this works. Some of this is tied to the claim that with sufficient data, standard machine learning training actually does a pretty good job of learning good features, which again, sufficiently describe the sort of context and setting that you're interested in making predictions on. And what fine-tuning does is just help you align your features to the particular target task. And this combination ends up being quite powerful in lots of different applied settings. Of course, I wouldn't be giving this talk if this is all I had to say, or maybe I would, actually, but I'm not. So it doesn't always work. Lots of examples where this can fail. I think saliently for us has been foundation models are growing. The context of which they're being trained are growing. But there's always a tail. There's always sort of more stuff than the model has gotten to see. And the more the task you're interested in is in the tail, the harder it is for sort of the existing paradigm of just let's scale things up out of the box tends to work. And so we have some examples. Here's an example from a translation task where we've been looking at sort of translations across subsets of languages. They're not represented in a large sort of training corpus, showing that there's still lots of cases where nominally, if you're I guess thinking about the problem generically as sort of foundation models by construction will solve your problem, we see a gap. Of course, if you look more deeply and handle the fact that there is, again, like lack of representation of the data that you care about in the training corpus, this explains reasonably why the gaps are showing up. And this shows up as, we call this a measure of alignment. You can think about this as a measure of the difference between the training setting and the deployment setting. So that's sort of, I guess, suggesting that there's still more that can be done. And so another setting that is also interesting is I may not have a ton of data in the target setting, but I'm willing to draw graphical models like we just saw. Well, the graphical models from before. So there you can use various kinds of domain adaptation methods. And it turns out, again, there's a good literature on this. And I'll show some work existing and some work that we've done trying to engage with this. So the most common version of these kinds of settings are covariate or label shifts. So these are typically predictive problems where the assumption that you're making is that your data distribution is shifted from training to the deployment setting, but the relationship between X and Y is stable. Or vice versa. There's a shift in the marginal distribution of your label, but in this case, you have an anti-causal prediction problem. I can give some examples in a little bit. And that version is stable. And there's a bunch of existing work on how to engage with these kinds of problems. They roughly boil down to massaging your data such that the unlabeled data that you see in the target distribution looks a lot like the labeled data that you've seen in the training distribution. So what this means is I didn't set context completely. So I have labeled data in my source. I get to see inputs and outputs. I'm interested in a prediction problem. In the target, I only get to see features. I don't get to see labels. And I either estimate the shift, and I know there's a shift, or something breaks, and this suggests to me that there's a shift, and I'm trying to break or figure out what to do to mitigate the shift. And so if I think the nature of the shift is a covariate shift, then it turns out reweighting is a good strategy. So you can do literal generic reweighting. Important sampling, these kinds of things tend to work quite well. There are also, I think, some clever adversarial methods that effectively achieve the same goal. So if you look through the methods, you can explain them as finding a good reweighting of your target distribution to look like your source distribution, such that I can use the model I already have in the source, and it will work out of the box in this sort of refined target. You can do the same thing if I have a label shift setting. So again, there's some massaging and a literature that exists and sort of tools that work well out of the box. Yet, in many settings, here I'm showing some examples in medical settings, but again, it wouldn't surprise me in lots of other settings. Label and covariance shifts are too strong and sort of insufficiently flexible for the kinds of shifts that we actually see in the real world. And what we're showing in this paper is a variety of settings where simply assuming label or covariance shifts are insufficiently or insufficient to actually handle sort of the kinds of shifts that we find. And so we've come up with some other methods, graphs, we like graphs, so other kinds of graphical models. The main takeaway here is that there are methods that allow you to correct for much more complicated concepts or latent variable shifts. Generally, you need a bit more information. So here we show, for instance, that if I have a latent shift in this healthcare setting, we're interested in shifts that are caused by things like socioeconomic determinants of health. What we show is that if you have some proxy of that latent shift, so you don't get to see the thing that's causing the shift, but I get to see some like a patient age or other kinds of demographics that are related to the underlying concept. This is often enough when we show that there are ways you can construct methods that first will actually show recoverability, so existence of like some distribution that undoes this shift or does the reweighting appropriately, and then we can show methods that allow you to get robust prediction. Finally, there are a bunch of these settings where what you care about is not adjustments to what you get to see at test time, but I really want to get a robust model that will be good almost no matter how my distribution changes. And so this is generally called domain generalization. I won't go into any detail, but I mentioned that this is something we've looked at. We have some methods that try to engage with this, and we show that in many settings I can come up with a special kind of regularizer inspired by the sort of causal graph that I showed earlier that will allow you to correct or allow you to build domain general predictors. And you think about this as like selective features that are stable, even though the distributions are changing. It's worth saying that this is not a free lunch. I like to highlight this. So domain general models are good for ensuring that you're robust to worst case kinds of shifts. So things that are essentially non-causal changes in the model. But if your shifts are benign, they generally will do worse in domain, but at the cost of robustness out of domain. And so I like to mention this explicitly because it's important for this decision of like, really figuring out what you care about. If you really do care about sort of robustness, generically, again, I don't have enough context here to think about the right framing here, but I think that'll be a good conversation. Predictiveness in domain versus robustness to sort of different changes in distribution. Okay, so that's the main takeaway, the full taxonomy that I talked about with sort of work along the way. The sort of TLDR is still a AI problem. There's lots of work in sort of extrapolation, interpolation-like things work pretty well. Fine-tuning can work pretty well. The more your problem looks like extrapolation, the harder it is. But if you're willing to make various kinds of modeling assumptions or have modeling assumptions that you can make, or you have data that you can use to fine-tune, often this can be a way to mitigate some of these issues. Okay, I'm done.
Not a real question. I'm taking notes. We're going to go back one slide.
Sure.
Thank you.
I'll start while people are thinking. So this example you gave where you have some correlate like age, which that's a good intuitive example where obviously that doesn't necessarily include all of the social determinants of health, right? So how are you figuring out how much of it includes or doesn't include, and is there some generic way to think about that?
There is. So the short version is that, or maybe the technical properties are all specified by the graph itself. So whatever this correlate is, needs to be caused by the latent shift, but sort of conditionally independent of the rest of the graph. And if you have that property, then you can use it to undo the shift. If it ends up correlated, so again, this either is via test or via domain expertise kinds of conversations. But if you can come up with some proxy that has this property, then we can use some of these methods as a way to mitigate the shift. So I guess there's a technical explicit property that needs to be satisfied.
Another question? Come on in.
I'm sorry, maybe too far, but there's one problem in cosmology where we're facing this kind of challenge of interpolation, extrapolation. I tried to show this animation where you have the dark matter and the baryons, and surprisingly enough, we know much better where the dark matter is than where the normal matter is. And that's actually a limiting factor in our ability to analyze logical structure data. We don't exactly know where the baryons are. We're able to generate a bunch of simulations with different models that would be different versions of where the baryons could be, but we're never too sure if those simulations span the whole range of possible versions of the baryons. I wonder if
that's interesting.
we might benefit from something like this.
I mean, in principle, yes. I think I need meaningfully more context on this. Yeah, I worry about saying something really stupid. Maybe that's actually the point. Brainstorming is to say stupid stuff here and fix them. It's recorded, so I can't say anything too stupid. It's just chat offline, I think.
Yeah, it's definitely very worth discussing.
Yeah, no, this sounds very much in the...
in our field.
Yeah.
All right, thanks, Sanmi.
Yeah, thank you.
All right. Hi, everyone. My name is Storey-Fisher. I am a postdoc at KaiPAC, and I'll be talking to you today about one method that we are thinking about for analyzing all of this beautiful data that we've heard about so far, simulation-based inference for 3D galaxy clustering. And this is work with Raul Angulo, Marcos Palajero-Ibanez, and Mateo Zanaro, and others that I'm continuing. Okay, so as we've heard a bit, the 3D distribution of galaxies traces the invisible matter underneath. It's called dark matter. So dark matter is on top, and underneath we see stars begin to form in the knots of the dark matter. So that's how we are going to infer the underlying matter distribution, and that's important because the distribution of matter is what encodes the cosmological parameters that we're interested in. So here is a simple example where on the top I'm showing a cosmological simulation that has stronger fluctuations of matter, so it'll have stronger knots of this dark matter, and then on the bottom, weaker fluctuations, but with the same initial conditions. So by looking at the stars and galaxies, really, that trace this matter, we can then go work backwards and infer the cosmological parameters that we're interested in. So quickly, the data I'll be focusing on today is these 3D maps of galaxies. So this is beautiful data from year 1 of the DESI survey, which is continuing to release data. And we can use this data and our simulations that I showed you before to try to understand these parameters that we care about, like like how much dark matter there is and how it's evolving over time with dark energy. Okay, so just briefly, I'm going to talk about how we traditionally do inference with this data before I get to fancy new methods. So we start with some prior of our expected value of the cosmological parameters, and then we model what we call summary statistics analytically. So these are a bunch of power spectra that we think we know how to model given these input parameters. Then we can write down a likelihood. We assume it's Gaussian, as Manu was discussing. We have to estimate the covariance in this case, which is very non-trivial. And then we can take our beautiful survey data over here, compress that into the same summary statistics that we used, and then sample the posterior with something like Markov chain Monte Carlo. So this is how we typically do it, but there are some issues here. So one is that as our observations get kind of more complicated in the types of galaxies we're observing, for example, the systematics in our observations might be hard to model in these analytic methods. We also know that the data is not necessarily Gaussian, or the likelihood is not Gaussian, as we've been talking about. And finally, by compressing our beautiful 3D map of galaxies into these like 30 bins of this summary statistic, we're losing a lot of this really rich information. So the idea is we can use simulations and the full power of our modeling to try to directly infer the parameters instead of having to go through some of these steps. So simulation-based inference on the same kind of map. We start with our prior once again, but now we run these powerful cosmological simulations, which we understand quite well. It's just gravity. We model how galaxies populate this dark matter, like on the first slide. Then we can compress this distribution of matter into more optimal summary statistics that actually contain all the data that we're going to get our parameters out of, or all the information. We train some neural network method to learn the distribution or the posteriors. So Sydney will talk about one particular method in the next talk. I'll talk about one on the next slide. And then we can send our data through to directly infer the posteriors. Of course, this also comes with some issues. On the good side, we have a pretty small space of target parameters that we care about, but we have very high dimensional data that is really slow to generate on the cosmological parameter side. And then we just discussed that it's a difficult problem to model how the galaxies populate this dark matter, so we have to marginalize over that. The data, finding a good summary is important, and finally, we really have to get this precision right. So SBI is a whole kind of suite of methods and ideas to try to solve some of these problems, but we introduce new problems. So these are the particular ones for kind of this cosmological inference setup. And with my last 30 seconds, I'll just kind of flash exactly what we're trying to do here. So because simulations are expensive, we actually use a machine learning emulator to generate our data. So that's relevant to an earlier talk as well. Then we use things called moment networks to try to directly estimate the moments of the posterior and marginalize over all of the high dimensions of our problem that we don't care about. the mean and the covariance, and so it's Omen networks all the way down. And finally, we can recover our parameters pretty accurately on a test set. That's all I'm showing. Okay, so that's all. Simulation-based inference will hopefully let us leverage the full potential of our data. Thanks.
Question for Kate?
Can you comment on the summary statistics you derive with your method? Do you select them? How do you select them?
Yeah, so what we can do is use a convolutional neural network on our data to kind of in the same process as we're trying to learn the parameters to learn the summary statistics. So those are an intermediate kind of layer that you can extract, but really you're learning it all at once and that's what makes it optimal for your problem.
One more question for Kate?
Joy, how easy it is to get the mean galaxy view?
So estimating the mean is fairly doable. It gets harder and harder as you want to estimate the higher moments of the distribution, which we really care about in cosmology, is estimating our uncertainties. So that you require a lot of data and good networks, and so that's right now the kind of the challenge for us. But the mean, we can do a pretty good job, actually.
Okay, thanks.
All right. Hi again, everyone. Today, I'm just going to tell you about a part of the analysis that a group of us at SLAC are really interested in, which is using strong gravitational lenses of quasars to measure the expansion of the universe. And I'll be specifically focusing on mass modeling using simulation-based inference. Okay. So I'm just going to quickly set up the problem again. So this is a video of a strong gravitational lens of a quasar. So you have a quasar in the back, a galaxy that's kind of along the line of sight in between us and the quasar. And what happens is the light from the quasar gets distorted into multiple images of the quasar. And what I'm very interested in is learning more about the galaxy that's doing the lensing. And in particular, I'm interested in looking at an image of of this system, and from that image, inferring properties about the mass. Not sure how to, there we go. Yeah, so I have that set up here. So from an image, I'm trying to infer the mass profile of the galaxy, and I'm gonna make that easier for myself by parameterizing that mass profile. And I'm just showing you two parameters here, the Einstein radius and the density profile slope. And so these are two of the key parameters that I'm trying to infer from an image of the lens. And so yeah, traditional methods, kind of like Kate showed, depend on very expensive likelihood computations. And so when we're moving from working with like on the order of 10 lenses to on the order of 1,000, we're trying to use simulation-based inference to get the speed up that we need to make this analysis possible. And so we've been doing something called neural posterior estimation. Basically, we generate a large amount of training examples using simulations that a network learns from to do approximate inference of a mass model posterior. So on the left here, this is the true posterior for the mass model. And on the right here, I learned some network weights, phi. And then when I pass an image through the network, it produces an approximate posterior for the mass model. And then this kind of goes back to something that was discussed earlier. One thing that we've kind of noticed is we are also kind of worried about the volume of training examples and spending too much time on training examples that are not very informative. And so we've also introduced sequential neural posterior estimation. And so basically based on whatever the initial guess is from this broadly trained network, we'll kind of fine tune based on that initial guess and retrain networks that are kind of in the neighborhood of where we think the answer is. And so we found that we get some better performance with this technique. So I only have time to show you like one example of something that we're investigating. Kind of the most exciting thing that I've been working on recently is an application to real HST data. And the most interesting part of this is we're training on simulations and we're testing on data. And we're really interested in seeing how robust we are to that shift, because the only option that we have is to train on simulations. We don't have the option to train on real data. And so I'm showing here just the lenses that we're testing on. And so first I'm going to show you the, basically based on the mass model that we infer from the neural network, we predict where the images of the quasar are going to show up. And so what I'm showing in the red stars here are if you just take the mean of the posterior. And I want you to take notice of this one right away. I'll come back to this one later. This is like one of our worst performers. And then, like I said, this is a posterior, so if we just take samples, what you can get an idea of here is how confident the network is in its prediction. So for something like this, it's a bit more confident. For something like this, you have more uncertainty. And so, yeah, just going back to this one here, what you'll notice is there's tons of like structure in the arc here, and that's not something that we're currently including in our training simulations. So this kind of brings me to my future directions. One thing that we're thinking is going to be necessary now is kind of increasing the realism of our training simulations, and I'm currently thinking about like building a generative model for how we can build a prior for what kinds of galaxies are producing all the structure we see in those strongly lensed arcs. As well as, yeah, so glad we talked about distribution shift. I'm very worried about distribution shift. Astrophysical observations have tons of selection functions on them. Super happy to talk about that. And yeah, as mentioned, more flexible functional forms than Gaussians for sure. So yeah, thank you.
Questions for Sydney?
Yeah.
Do you have a sense of the physics, like in your mind, do you have a mental model of the physics that's causing the kinds of observations that you see that the neural network really underperforms on?
I think it has, yeah, so I think it has more to do with kind of like the structures that are seen, not necessarily in the mass model, but in some of like the nuisances. So like for us, like when we're producing the mass model, we're not trying to infer what the light is in the host galaxy of the quasar, but it might actually be really degenerate. So for example, like the width of the arc is degenerate with like the size of the host of the source galaxy and the density slope of the mass. So those kinds of like degeneracies, like if we're not capturing the full range of the size of the source correctly, that could introduce problems in the thing that we do care about, which is the mass modeling. Yeah.
More questions for Sydney? All right, let's thank all of our speakers.
Well, you're all going to have to answer this question because we have one more sticky note based exercise for you. So locate some nearby sticky notes and markers, share with your neighbors. And we're going to ask you to just think about and write down one new thing that you learned today. That can be from the talks, that can be from your conversations. What's one new takeaway that you have, one new thing that you learned? And then write it down and stick it on the wall. Thank you.
Once you've put your sticky note, and you're welcome to still do the first exercise, which is what you actually want to work with people in the room or out of the room on, then we will have food and drink outside. So that is your incentive to make your sticky note.
Yes, your meal ticket is the sticky
thank
note.
you. This was super, super fun. So I personally learned a lot, and I want to again thank Laura and the rest of the staff in the back of the room for making an amazing